We're going to start off this lecture with a warm-up problem that will eventually tie in with the rest of today's topic, which will be minimum spanning trees. So my question for you is, given an undirected graph, figure out, does it contain any cycles? And you can use any data structure, any algorithm you've seen in the course so far, depth first search, whatever seems useful. So I'll let you think about that for a little bit, and then I'll give you a couple of potential answers. So think about that for a minute or two or 5. I'll be waiting. Okay, so a couple of answers I had in mind, but maybe you have something else. One is, we could just use depth first search from some arbitrary vertex, doesn't matter where you start, and then you just keep going until you see a marked vertex. So for example, I go 0, 1, 3, 6, 5, 4, oh, 6 already marked, so that means that there must be a cycle. Now, one little caveat with this approach is you need to be careful by what you mean by looking at neighbors. So if I run depth first search and I look at 0 and then go to 1, if I look back and see where I just came from and call that a cycle, that's not correct, right? This is not, a line does not count as a cycle. So the solution to this is just don't count the node you just came from, and that'll work just fine, okay? So that approach will work, and as long as the graph is connected, then this approach will work for any start vertex. And in this case, the worst case runtime for this algorithm is just v plus e, and that's because it's basically just depth first search. And if that's not something that's immediately obvious to you, make sure you're going through and doing the B-level study guide problems for graphs. Now, an alternate approach, which is arguably a little more intuitive, is using a weighted quick union object, or just any kind of disjoint sets tracking object. So what we'll do in that case is, for each edge, we will check to see if the two vertices are connected. So I iterate through all the edges, and I say, okay, are 0 and 2 connected? If not, we'll union them, thus establishing that they're connected. And if they are already connected, so suppose I do union 4, 6, union 4, 5 is connected 5, 6. This will return true, and since we haven't used this edge yet there exists a way to get from 5 to 6. That means there exists a cycle. So this approach also works. Now the runtime of this approach is going to be v, because we have to go through we have to create a weighted quick union object of size v, so that takes time v, and then the time to do all the union and connected operations is going to be e log star v. And if this isn't immediately obvious, well, later in lecture when we talk about an algorithm called Kruskal's algorithm, it'll become clear why this is e log star v. Okay, so that's our warm-up exercise for the day. So let's get started with today's topic.